Chapter 16, Lesson 3. In this chapter we've been talking about acids and bases, and here we'll talk about the pH of acidic and basic solutions in a little more detail. So we talked in Chapter 4 about the 7 strong acids, and these are kind of recognized as the strong acids, meaning that they completely break apart in solution. They, recall, are the 3 binary acids: hydrochloric, hydrobromic, and hydroiodic, and the 4 oxyacids: nitric, sulfuric, chloric, and perchloric. All of these are very strong. And if they're strong, this means in aqueous solution they completely break apart. So HCl, for example, completely breaks apart into H plus and Cl minus. And what you've got yourself is a bunch of hydrogen ion and chloride ion in solution. But because we said that hydrogen ion is really the same as H3O plus, this is hydronium ion, what we can say is that for strong acids, the hydrogen ion concentration is the same as the concentration of the acid, because every little amount of acid breaks completely apart into H3O plus. Likewise for the strong bases, most of the strong bases are your hydroxides, your soluble hydroxides. So the alkali metal hydroxides like sodium hydroxide is the famous strong base, potassium hydroxide, and so forth, and then including the alkaline earth metal hydroxides, as long as they are soluble. In fact, these 3 are the exceptions to the solubility rules of hydroxides. So magnesium hydroxide is not generally considered to be soluble, but calcium, strontium, and barium, these are the 3 robbers. If you recall, they are soluble. Not very soluble, slightly soluble, but the amount that dissolves completely breaks apart in solution. And it should be noted that when calcium hydroxide dissolves and separates, what you get yourself is you get a calcium 2 plus ion, and you get yourself 2 hydroxide ions. This is actually pretty important. These 2 will influence the acidity or basicity of your solution. You get twice as much hydroxide per mole of calcium hydroxide than you would for something, say, like sodium hydroxide. So now, along with these concepts, we can ask about the pH of acidic solutions. Here we have the pH of a 0.040 molar solution of nitric acid. We know that nitric acid is a strong acid, and since it's strong, every mole, every amount of it will dissociate. So what you'll find is that the amount of H plus in solution is exactly the same as the concentration of the acid, namely in this case 0.040 molar. And because pH is the negative log of the H plus concentration, we can simply negative log this number, negative log 0.040, and we should get ourselves a value. Go ahead and try this on your calculator. Oftentimes you have to put the number in first and then click the log and then click the negative. And you should find yourself having a pH of 1.397 or 1.40. And recall that pH is unitless. Now let's try the same thing with a base. We have ourselves a 0.011 molar solution of calcium hydroxide. Now you'll recall from the previous slide that calcium hydroxide provides 2 moles of hydroxide. So your hydroxide ion concentration will actually be 0.011 times 2, or 0.022. So when we get the pH, we have to make sure we consider both hydroxides, because when calcium hydroxide dissociates, it produces 2 ions of hydroxide. Now, in order to get the pH of a basic solution, there are a few things we can do. I would suggest first getting the pOH, POH, recall, is defined really the same way as pH, except it's the negative log of the hydroxide ion concentration. So in this case, we've got negative log of 0.022, which gives us, go ahead and plug this into your calculator. You should get yourself 1.66. Now this is the POH. We want the pH of the solution. And recall that to get the pH from POH, you simply subtract from 14. So pH will be 14 minus 1.66, which should get you 12.34. And this is the real answer. 12.34 is your pH, which is consistent with a basic solution. Calcium hydroxide is a base, so we would expect a high pH, above 7, quite a bit above 7, which it is in this case. And that's how you get the pH of actual basic and acidic solutions. Next we're going to talk about dissociation constants. Now these constants essentially are the same as we've seen in the previous chapter, except now we're going to apply the equilibrium constant to acids and bases. So we've seen the acid reaction, because acids donate protons. We've seen that we can write out a reaction where an acid reacts with water to form the conjugate base and the hydronium ion, and if we plug this into our equilibrium constant, we will get a picture like this. Now recall that liquids do not go into the equilibrium expression, and that's why we ignore water. But all the rest, since they are aqueous, go into the equilibrium expression. So this is the standard way of expressing K, as we've seen in the previous chapter. So, looks like we skipped a bit ahead. And we have a special designation. When we give an equilibrium constant for an acid reaction, we designate the equilibrium constant as Ka, K sub A. These are specific for acids, is the idea. And a similar thing can be done for bases as well. So Ka's will express for you the dissociation of that acid, the strength of that acid. So here it says the greater the value of Ka, the stronger the acid, which makes sense because we said high values of K, because remember K is products over reactants. So if you have a high value, big value, that means you have a lot of products and a little bit of reactant. In this case, your weak acids will usually have tiny numbers for K, but their relative values can still tell you how strong the acid is. So in the case of nitrous acid, your Ka is 4.5 times 10 to the negative fourth, which is a small number. However, acetic acid is even smaller. Acetic acid is 6.3 times 10 to the negative 5. So you see that acetic acid has a smaller Ka, therefore it is weaker. Remember, if this is a tiny number, that means the products, there's just a little bit of products at equilibrium and a lot of reactants. So the smaller the Ka, the weaker the acid. You can say smaller Ka, weaker acid. And vice versa. The stronger the acid, the higher its Ka value. And generally for very strong acids, we don't consider Kas because their Kas are so huge, in the tens of thousands if not the millions, that we just ignore. We say it's completely dissociated. So what we like to do here then is do a calculation of a Ka from pH. In fact, this will require the use of something we've seen before. So this is a single diamond problem, which means we will have to use the icebox. These are your icebox analogs from the last chapter applied to the acid and base chapter. So we have a pH of a certain solution of formic acid, and here's the formula for formic acid, and the pH is 2.38, and we're asked to calculate the Ka for formic acid. So this is very similar to what we did in the previous chapter, where we were asked to get the K of a reaction for which we knew the initial concentration and the equilibrium concentration. Now in this case, the equilibrium concentration is going to be given to us in the form of a pH value. And from the pH we can find out the concentration at equilibrium of H+. So why don't we try this example on the next page. We've got ourselves formic acid. Let's go ahead and write out the equation for formic acid. Now formic acid is written a bit strangely. There are two ways we can do this. We can either add water, as we've done before, so why don't we do that? And this will be an equilibrium. Since formic acid is an acid, it'll donate a proton, and I will show when the formic acid is written out in this way, oftentimes the back H is shown to dissociate. So I will show it as HCOO-. If this confuses you, don't worry too much about it. If you would have put the first H, I would have accepted it full points. But commonly, this is an organic version of it, so it is shown, the H at the back is shown to come off. And then what's left, since the H was donated to water, water becomes H3O+ or hydronium. And now we can set up the icebox as we've done before. What we're given in the problem is we're given an initial concentration of our acid. In fact, the 0.10 is our initial concentration. We'll assume the products to be 0 always. We've done this in the previous chapter, and in this chapter we'll always assume these to be 0. The water is a liquid. Now we said liquids don't really go into the equilibrium expression, so we don't really care about this portion of it. You could put things in there, but it will not go into the K, so we don't really care. An additional piece of information given to us is that the pH of this system is 2.38. Now, what this means is that when this reaction has come to equilibrium, when all of the H has dissociated, the amount that's dissociated at equilibrium is hidden in here. Now remember, pH is simply the negative log of H+. So there is a way to find the H+ of the system. And if we undo that, we showed you this last time, H+ can be given as 10 to the negative pH. So by undoing the pH, we can find out how much H+ we have in the system. And this will give us the value, the equilibrium value right here. This is the equilibrium value. Remember, H+ is the same as H3O+. So this will give us how much there is of hydronium ion in equilibrium. So pH is connected. pH is connected to this portion of the equilibrium. So if you do in your calculator 10 raised to the power of negative 2.38, you should get yourself, let's go and write this out, 10 to the negative 2.38 should give us 0.00417 molar, and that's the H+ concentration at equilibrium. So we can go ahead and put that in here, 417. So we have an equilibrium concentration, we have an initial concentration. This version of the icebox, we can fill the rest of the information in, and we'll get ourselves the necessary information to then solve for our K. We know that to get to equilibrium, we must have added 0.00417 here. Since it's a 1-to-1 ratio, this substance here, the conjugate, will also be plus that amount. So we end up with 0.00417. And then we know, since it's a 1-to-1 ratio, we must have lost this much on the original acid concentration. So if you do 0.10 minus this value, we get ourselves 0.09, 583. And now, in order to get the K, recall K is products over reactants. In this case, the K would be your H3O+ concentration times your HCOO minus concentration divided by your original HCOOH concentration. So plugging the values in, we should get ourselves something like this. We get 0.00417. This number gets squared, again because of these values. Remember, these are the values that will go into the equilibrium expression, the equilibrium concentrations, divided by our reactant, 0.09583. Plug those numbers in and see what you come up with. And you should get yourself 1.81, or 1.8 in this case, 1.8 times 10 to the negative fourth. And this is the Ka of the acid. So to review, what we did is we were given an initial concentration of our acid, and then we were given the pH of the acid. The pH indirectly told us how much H3O plus, because pH checks how much hydronium ion you have in solution. That gave us how much hydronium ion we have at equilibrium, and then knowing these two facts, we were able to fill the rest of the icebox in, plug the icebox, and solve for Ka. This is a very important problem to be able to solve, so we'll have a few of these practice problems for you. We'll finish up this discussion with a percent ionization calculation, and this is quite simple. What we do is very often, instead of giving the Ka of an acid, Kas are very tiny. In the previous case we had 1.8 times 10 to the negative fourth, and sometimes it's hard to see really what this number, how much of the acid is dissociated. Even though this tells us how much is dissociated, it's hard to visualize that, and sometimes we like to see it more in a percent way. So what we'll do is your H3O plus concentration at equilibrium will be divided by your initial concentration, and then this will give us the percent. We'll multiply by 100 and we'll get the percent. So why don't we do that for the next, I think on the next slide. Yeah, we're asked to calculate the percent ionization for the 0.10 molar formic acid solution that we worked. So percent ionization, we said, is simply the initial concentration divided by, the equilibrium concentration divided by the initial concentration. So H3O plus over the HA initial, and then times 100. So our initial is actually 0.10. Our H3O plus came from our pH, and we decided that was, if you recall, let's go back real quick here, that was our 0.00417. So we got 0.00417 divided by 0.10 times 100. So plug that into your calculator. Essentially we're multiplying by 10 and then by another 100, so which gives us about 4.17%. So what you're saying is that roughly 4% of the molecules of your acid break up into H plus and the conjugate. So if you have yourself an acid dissociating into A minus and H plus, about 4% of this acid breaks apart and goes on to the product side. So this is a better way to see it, and essentially it comes up or comes from your Ka. Your Ka is connected to this value. And this concludes for us lesson 3 of chapter 16.